So this is a review of radioactive decay. How many types? Three. But kind of? Four, kind of, right? So we have alpha decay. An alpha particle is really a helium nucleus. 2 protons, 2 neutrons, atomic mass of 4, and it's going to go bye-bye and fly off of our nucleus. So the example would be a uranium-238. It loses an alpha particle. This is the alpha particle, flies off, and what you're left with is a thorium nucleus. So this is going to change the element. The mass goes down by 4, and you have an alpha particle. Pretty common decay. Then we have beta decay. There are 2 types of beta decay. There's beta positive decay and beta negative decay. Beta negative, much more common. So if you're taught beta decay and you only get 1, it's probably beta negative decay that you're being shown. Just to be clear, the word nucleons equals protons or neutrons. Whenever we talk about those particles in the nucleus, we're talking about nucleons. So let's start with beta negative. With beta negative decay, what's really happening is a neutron is becoming a proton. And when a neutron becomes a proton, obviously your atomic number goes up by 1. But your mass, your atomic mass, stays pretty much the same. Because we've added a positive charge, we have to also add a negative charge because our charge must be conserved. An electron is a particle called a lepton. There are 3 flavors of leptons: electron, muon, and tau. You'll learn more about those later. But our universe says you must conserve lepton number. So if you create something with an electron flavor, you must also create something with an anti-electron flavor. And so this is an anti-electron neutrino. So it's a neutrino, which is a neutrino. It's very small, very little mass, and neutral charge. And this one happens to be an antimatter neutrino. And that way we have an electron-flavored matter and an electron-flavored antimatter, so that conserves our lepton number. And because there's no charge here, we created a positive and a negative, so that's fine, everything's chill. So charge is conserved and lepton number is conserved. An example is carbon-14. This is what we use for carbon dating and living things. Because over time, this decays into nitrogen. We know the half-life is, I think it's like 5,000 years and something like that. So it's kind of a nice age for living things. If you want to date like a fossil or a bone or a tree stump or something like that, you can get the portion of carbon because it's continually being processed when you're alive. All of us would have very similar portions of carbon-14 to carbon-12, but then once you die, your carbon becomes fixed and then this starts to decay, and so you have less and less of that isotope as the years go on. Beta positive is less common, and you might not even get taught that when you're being shown this the first time, except if you're unlucky and you're taking IB physics. You have a proton this time becoming a neutron. I don't know if you want to know this, but you put your hand up to know more. So when this happens, what's really happening is you have 1 quark that is being transformed. So a proton is made of 3 quarks, and a neutron is made of 3 quarks. Does anybody know the 2 types of quarks in protons and neutrons? Good. Up and down. Up, up, down is a proton, and up, down, down is a neutron. So you take one up quark, it turns into a down quark, and you go from proton to neutron. Don't worry about that. We'll look at that more later. For now, a proton becomes a neutron. We've lost a positive charge, so we have to create a positive charge. So we also create this crazy particle, which is a positron. This is the tricky one. IB will trick you with this because this is antimatter. Normally, antimatter has a line drawn over the top, but they probably will not draw the line, and they'll just call it a positron. The nicer thing to do would have been to name it the anti-electron, but it's not called an anti-electron, it's just called a positron, and everybody's supposed to know that this is antimatter. And it has a positive charge, which is cool because we lost a positive charge, so now we gained a positive charge, so now everything's cool. This is antimatter, and it's an anti-electron flavor. So we have to conserve the lepton number. So if we create an anti-electron flavor, we also have to create an electron flavor to keep our lepton numbers balanced. So this is a neutrino, but this time it's not an antineutrino, it's like a matter neutrino, and it's electron flavored, so everything is chill. An example of this is carbon 11. We'll go through beta positive decay, and it'll become boron. It goes down one number, the mass stays the same. And we have our positron and our electron neutrino. The last type of decay is gamma decay. Gamma decay will often accompany another type of decay if you need some energy released, and it's just a high energy photon. Those are the types of decays. We'll go into it in a little more detail later, but that's enough for now.